Is it going? Okay. All right. So again, this is page 429. We're going to do questions 27, 33, and 41. So question 27 is asking, how is the law of combining volumes explained by Avogadro's hypothesis? And then it says, consider a 1 liter flask containing neon gas and a 1.5 liter flask containing xenon gas. Both gases are the same pressure and temperature. According to Avogadro's law, what can be said about the ratio of number of atoms in the two flasks? All right, so anyways, one of the things that I didn't get to talking about yesterday was that if I have a reaction like the one that's here, where you have nitrogen gas reacting with hydrogen gas to make ammonia, the coefficients in front, in the past, we understood that the coefficients represented moles. So according to the equation, 1 mole of nitrogen with 3 moles of hydrogen ends up making 2 moles of ammonia. Okay? All right. When it comes to gases, and if you look at this equation, all 3 of these substances are gases, right? The nitrogen's a gas, the hydrogen's a gas, and ammonia at room temperature is a gas as well. These coefficients also represent volumes. Okay? So you could also read the equation this way. You could say that 1 liter of nitrogen plus 3 liters of hydrogen makes 2 liters of ammonia. And in essence, that's Avogadro's hypothesis, is that you can extend these coefficients to the volumes. You can make volume ratios out of those coefficients. Now, that's only true if your pressure and temperature are kept constant. If your pressure and temperature change throughout the process, you can't say this anymore. You can't make these volume proportions. Okay. All right. So let's take a look at part B. It says consider a 1 liter flask of neon. So a 1 liter flask, and a 1.5 liter flask of xenon. Both gases are at the same pressure and temperature. According to Avogadro's law, what can be said about the ratio of the number of atoms in the two flasks? What can we say? Does one flask have more particles than another? Which one? Which one? It's 1 and 1.5. They're at the same pressure or the same temperature. Does one have more particles than the other? Yeah. Which one? And I can say that provided both of those flasks were the same pressure and temperature, right? Mathematically, how could I prove that? Do I need to prove that to you? No, not even. This isn't part of a reaction. They're two separate flasks. Could you substitute, like, say for instance, say we decided to assume that the pressure and the temperature that I was using was standard temperature and pressure, right? Which would be a pressure of what? What's standard temperature and pressure? What's standard pressure? 1 atmosphere. And a standard temperature of 0 degrees Celsius. And well, let's say we have this gas also under the same conditions. How can I prove that there are more particles here than there are there? Is there an equation that I could use to prove that? What equation would that be? PV equals nRT, the ideal gas law. Okay, I could use PV equals nRT over here, PV equals nRT over there. Okay, so let's substitute some of these numbers for neon over here, and some of these numbers for xenon over there. Okay? All right, pressure, 1. Over here, same. Volume, 1. Over here, 1.5. We get N. What's R? 0.0821. What's the temperature on the left? In Kelvin, what would that be? 273. Okay. How do I get N by itself? N would be, how do I isolate N over here? 1 times 1 over 0.0821 times 273. All right? Okay, let's finish it off over here. So the pressure was 1, the volume was 1.5, and I don't know, what's R over here on the right? 0.0821, and what's the temperature over here on the right? 273, because I'm looking at it under the same conditions. How do I get N by itself? It's 1 times 1.5 over 0.0821 times 273. Not that I actually have to put these numbers in the calculator and simplify. It's pretty obvious to tell that one of these is going to be a bigger value than the other one, right? Which one's going to be a bigger value? Because it's got a bigger numerator, right? Okay, make sense? Now, what does that have to do with this shenanigans? With this Avogadro's hypothesis that I introduced at the beginning? Does this not just say that more particles yield larger volumes? Does that not prove that? More particles, right? This has more particles than that. Has a larger volume than that. Provided what? Pressure and temperature are kept constant. Okay. Why would more particles have a larger volume if pressure and temperature are constant? Exactly. Volume would have to be larger in order to accommodate for pressure. Okay. All right, that was basically all they wanted for question 27. It's a very simple concept. All right, let's take a look at number 33. To be honest, you could have gotten by in life without really knowing Avogadro's hypothesis, because we can do all the calculations that we need to be able to do straight up from the ideal gas law anyways, and prove it to ourselves. All right, so 33, they wanted us to complete the following table for an ideal gas. All right, I'm not going to do all of it. Just tell me which one you needed help with. A, B, C, or D? Who wanted this one?
I said artistic, but I forgot the number.
Oh, so this one down here? It's okay, we'll do it. Because, if you're asking the question, Cameron, I'm sure someone else in the room wants it too. All right, let's take a look at 33. I think it's a perfectly good example for what I need to talk about. All right, so you see there's a table. You have to complete the table. They gave me pressure, volume, moles, and temperature. Oops, my finger slipped. All right, anyways. Anytime that you are given moles or they ask for moles, right? Kind of off page. All right, anytime they give you moles or they ask for moles, that's the big old red flag that the equation that you should be using is the ideal gas law. All right? Now, they were nice, and in the question, they were kind of trying to guide you to using that equation by telling you that it was for an ideal gas. All right? So they were trying to give you an extra clue as to what equation is used. But you didn't need that information because just simply seeing that there's a column for N, you know to use the ideal gas law. All right? All right, so what is the ideal gas law? What is it? PV equals nRT. All right, so I'm going to do the fourth part of the table. So we're going to call that part D, even though they didn't label it that way. So in part D, they tell me that they don't know the pressure, but they want it in atmospheres. They do know the volume. The volume that's given is 585 milliliters. They know the number of moles is 0.250 moles. And they know the temperature. It's 295 Kelvin. All right? When I use this equation, and even when I use any of these equations, what I like to do first is I like to figure out what variable I'm really going after, and I like to go ahead and isolate the equation for that variable. All right? So how do you get P alone in that equation? P equals nRT over V. Okay? I do this because I have a tendency, if I substitute first, I have a tendency to multiply the wrong numbers together and divide the wrong numbers together because I'm usually doing this kind of in a rush at 10 o'clock at night. You know, trying to take care of my children and my household and falling asleep. And I'm sure you do too, except for you do it at 3 o'clock in the morning on Skype.
No, not yet.
Not yet?
This semester.
All right, not yet this semester. All right, anyways. So I like to rearrange the equation first because it makes, it minimizes the math errors for me. Okay? All right, so, but here's the deal. So you know V, you know N, you know T. What about R? You know R? Okay, what is R? It's a constant. It's a number you memorize. It's 0.0821. That's great that you know that, but what I really need you to know is the unit, because the unit will dictate what you do for all the other variables. All right, so what is the unit for R? Anyone remember? Liters times atmospheres over mole Kelvin. All right, so because that's the unit for R, because it was derived by doing experiments in which the volume was measured in liters, the pressure was measured in atmospheres, and the temperature was measured in Kelvin, it dictates that all those other variables be in those same units before you shove those numbers into that equation. All right, so let's take a look. Is the pressure in atmospheres? Well, yeah, they want it in atmospheres. Is that consistent with that? Absolutely. All right, what does the volume have to be in? Liters. Is it? No. How do I change that to liters? You divide by 1,000. It should be 0.585 before you substitute it into the equation. How about that? Is that the right unit? Is it consistent with R? Sure. How about the temperature? Is it consistent with R? Yeah. So that's the first thing that you have to do, is to make sure that the numbers that they give you in the table are consistent with the units for R. If they are, you can go ahead and substitute in. If they're not, you change them. Okay? All right, so let's substitute now. So N was 0.250, R is 0.0821, T is 295, V is 0.585. And you'll notice this is 3 sig figs, 3 sig figs, 3 sig figs over 3 sig figs. So guess how many sig figs you give in the answer? 3. All right, so 0.250 times 0.0821 times 295 divided by 0.585. My calculator says, it says that. So how do I write that? How do I write that? 10.4. What's the unit? Well, I don't know. I can cheat. I can look on R. It'll tell me what unit. Atmospheres. What if the question hadn't specified what unit to leave pressure in? Leave it in atmospheres. Okay. Let me show you another one here. They didn't give an example like this, but what if they had asked one of these to be, for you to solve for the temperature, and they didn't specify to do it in Kelvin like in part A. They just said put a question mark under temperature. What would you do? Shove it in the formula. Do you have to go back to Celsius? If they don't specify, stay at the unit that R tells you you should get. Okay? If I had said, instead of giving me the temperature in Kelvin, if I asked for Celsius, then what would you do to change it from Kelvin to Celsius? Subtract 274. Okay? I guess what I'm trying to get across to you is, if they don't specify units, do the minimum work. All right? Leave it in whatever units you get out of the equation. You don't have to go to any other particular unit specifically to satisfy me. Okay? All right? Be sure that you know what the question's asking. If the question specifies Celsius, then unfortunately you're going to have to take that extra step and do the extra work. But if it doesn't, just leave it as is. Okay? All right, let's take a look at the last one, question number 41. 41, do I do all of it, or do you want me to do a particular part of it? Who needed this one? Which part? C? answer. It says chlorine is widely used to purify municipal water supplies and treat swimming pool waters. Suppose that a volume of a particular sample of chlorine gas is 8.70 liters at 895 torr and 24 degrees Celsius. All right, so that's information that I'm going to use for all parts. So I better jot it down. Okay. All right, so on my piece of paper here, let me write down. The volume is 8.70 liters, right? The pressure is 895 torr. The temperature is 24 degrees Celsius. Part C is asking what volume, at what temperature. All right, so this is the initial information, right? 870 liters, 895 torr, 24 degrees Celsius. Okay. So the question asks what temperature will the volume be 15 liters if the pressure is 8.76 times 10 to the second torr. Riddle me this, kiddos. Is it the same number of particles? Yeah, it is. They're saying I've got this sample of chlorine gas. It's a very specific number of particles in a container, right? And I'm going to take those same number of particles, I'm going to put them in a bigger container. I'm going to drop the pressure slightly. What's the new temperature of that system? Okay, well, there's a couple of ways of doing this, all right? One way of doing this would be to use the ideal gas law to figure out what N is over here, and then use that same N over here with these new conditions, use the ideal gas law again 2 times. That's one way of doing it. There's an easier way of doing it, though, right? Remember yesterday we talked about, like, what I showed you, Charles' law, Boyle's law, Gay-Lussac's law, and the combined gas law? And then we talked about the ideal gas law. And we talked about what are the red flags for figuring out which equation to use. All right, so Boyle's law, you would use it in the word problem. They give you either 2 pressures or 2 volumes. All right. Charles's law, you would use if you see 2 volumes or 2 temperatures, anywhere in that word problem. Gay-Lussac's law, you would use if you saw 2 pressures, 2 temperatures, anywhere in the word problem. The ideal gas law, you use if you see moles or grams anywhere in that problem, whether they ask for them or they give them. What are they giving me here? 2 different volumes, 2 different pressures. And they're asking for a 3rd variable. What equation do you think we're going to use here? You could use the ideal gas law twice, or what else could you use? You could use a combined gas law, which is P1V1 over T1 equals P2V2 over T2. It's the equation that combines Charles, Boyle, and Gay-Lussac all into one. All right? So these will be my initial conditions. These will be my final conditions. All right. Here's the deal, though. Before I put numbers in here, all right, I'm going to first start by isolating the variable that I don't have. All right? Well, how would you get T2 by itself? Well, how do you undo this mess of fractions? You could cross multiply, right? If I cross multiply, T2 P1V1 equals T1 P2V2, right? This times that equals that times that. How do you get T2 alone? Divide by P1V1. So T2 is T1 P2V2 over P1V1. All right. Now I'm going to plug numbers in. But the problem is I may or may not have the right kind of units. All right. Now, volume is consistent. That's okay. It doesn't matter what unit volume's in. You just have to be sure that the 2 volumes you put in are the same unit. Pressure is consistent. Again, it doesn't matter what unit of pressure you use. They just have to be the same on both sides. What's the problem with temperature? It's not Kelvin. So what is that in Kelvin? 24 plus 273 is 297 Kelvin. All right, now I can substitute these numbers in. I'm going to get a temperature. I'm just going to leave it in Kelvin because I'm lazy. It's not. It really isn't because I'm lazy. It's because I want to avoid making the mistake in the conversion. I want to minimize chances of having points taken off on a test is what I want to do. My pencil's out. Okay. All right, so let's take a look. T1 is 297. Let's substitute. P2 is 876. I don't know why they gave it to me in scientific notation. That's 876 anyways. V2 is 15.00. P1 is 895. V1 is 8.70. 3 sig figs, 3 sig figs, 4 sig figs, 3 sig figs, 3 sig figs. So who wins out there? 4 sig figs or 3 sig figs? 3. So whatever answer I get out of this has to be to 3 sig figs. Okay, what is that to 3 sig figs? Come on. What is that to 3 sig figs? 501. Units. It's temperature. Let's leave it at Kelvin. If it had specified to do it in Celsius, you subtract 273 from that. (228 Celsius). Okay? That's all you do. Are we good? Yes. Well, all the questions were based upon this specific sample of chlorine gas. The one thing that doesn't change in that sample is the number of particles in that sample. You can change the size of the container that it's in, you can change the temperature that it's at, but the number of particles is consistent. It's the same sample. Okay. All right. Are we good? Any questions? Okay, so let's stop that there. God bless. 22 minutes for 3 problems. Okay. Is it here? Don't tell me it's not even here. Is it still recording?